We're talking about the ascent curve, and what we like to proceed now is into the modeling stage. How can I model a line that fits this data as well as possible? So that's going to be our concern. But before we do that, let's quickly discuss some of the safety factors that we might be concerned with. So there are several safety factors in the case of fatigue. So first of all, we can have a safety factor on life. So let's call that xn. Or we can have a safety factor on stress. Let's call that xs. So this is on life, and that's the safety factor on stress. And the way they're going to be defined is as follows. So first of all, suppose we have a certain stress amplitude. So the stress amplitude is given. And for that stress amplitude, there is a corresponding fatigue life. That is NF. But of course, I don't want to cycle to that number of cycles because for sure failure is going to occur, if not then, perhaps even earlier, due to uncertainties. And therefore, I never want to cycle up to that value, but I want to probably do service if I don't have an endurance limit before that. So this is the fatigue life. And this here is the point where we somehow do either an inspection and subsequently decide to do service or perhaps do some fixing or replacement. The other thing I might do is the following. I might have a target life, so let's call that NF. We're going to call it NF. So NF is not necessarily a value that's going to cause failure, it's just my target. And if I want to reach that target, and if I want that to be associated in reality with failure, then the amount of stress I would have to apply would be a certain value sigma A. That would be the fatigue strength of the material for that given number of cycles. But of course, I don't want to apply that stress because I don't want failure to occur. So I apply a stress that is less than that value, and let's call that sigma hat A. So this is the fatigue strength. And this is the value at which you operate. You operate at a lower value and you end up with a safety factor that is larger. All right, so these are the two safety factors that one typically uses. So here, of course, either way you look at, there is a fundamental question, and the question is the following. So if somehow we can predict for a given stress amplitude the number of cycles to failure, so if sigma A given, if I have a model that is able to deliver NF, then within a given safety factor, so if the safety factor desired value is known, number of cycles to failure, fatigue life is known for a given stress amplitude, then I can determine when to do, we can predict when we want to do inspection. Okay, and that is basically the goal or the idea beyond modeling as we have done before. And in this case, we're shooting for a fatigue model. Now, the type of data that we have is one that is not necessarily a perfect data. In particular, if I were to go ahead and plot number of cycles to failure versus sigma A, even on a log-log scale, so normally we don't put a log here, but just for the present discussion, I'm just going to put a log, and I'm going to put an exclamation mark because one does not always do that. What we will observe is a line that is still quite curvy, okay? And moreover, that line might even have two limits, one that either goes like that or one that goes like that, depending on ever decreasing value depending on whether there's an endurance limit or not. Even if that's the case, right, what we're going to do is we are going to model a line through our data. A line that goes like this. Okay? And if it turns out that there's an endurance limit, we have to cut off that model. If there is no endurance limit, then perhaps we can continue that model. Either way, we're going to assume, ideally, that on a log-log scale, we have a line fit to a data that is not essentially a perfect line. So now, whenever on a log-log scale you have a model that is linear, then we know that in linear versus linear, then we have a power relation. And that's indeed what we're going to propose. We're going to propose that the number of cycles to failure is related to the fatigue life is related to the fatigue strength through a power relation. So the number of cycles raised to some power is going to be proportional to the stress amplitude, and therefore there will be a proportionality constant, sigma f prime, but it is usual to omit the number of, to count the number of load reversals instead of the number of cycles. So I'll put a factor 2 there, and that is the model that has been proposed. And this model has been proposed long time ago by Basquin. So this is the Basquin equation that governs fatigue. And therefore, if I know for a given material what the exponent B and the coefficient sigma f prime, what they are, then for a given target life, I can determine the stress amplitude, or for a given stress amplitude, I can determine the corresponding fatigue life. Now remember, emphatically, this is very important what we're doing presently. What we're doing presently is that we are looking at cases where, first of all, there is no stress concentration. The concentration factor is 1, in other words. And therefore, sigma m, the actual stress, is the same as the nominal stress. And moreover, the mean of those are equal to 0. So in other words, we are looking at a scenario that is completely reversed. So we're going to take the R of reverse, and at the very beginning of the discussion, at least in your book, there is no preference on putting an R, but I'm already going to put it here to remind ourselves that this stress amplitude is for reverse loading, and we're going to make use of it in that fashion. Now, and moreover, remember that this data is collected from this completely reverse, say, banding experiment, and therefore, when we are looking at the stresses, we are looking at only normal stresses, and in a 1D scenario, there is only one normal stress. So we have to remember the conditions under which data is collected and to which this Basquin equation is fit. All right. Now, Basquin equation is something that we just have to remember and that we will make use of, so we will keep that in mind, and we'll use it so often that that's not going to be very hard. Let me just mention at this stage that this is not the only way, the format in which you see the Basquin equation. What matters is that there is some proportionality between the number of cycles to failure and the stress amplitude. So another way to write this would be A, some coefficient A, and f to the power b. Now, of course, these two forms are entirely equivalent, and therefore you can deduce that, first of all, the coefficient b, capital 1, is equal to the small 1, and moreover, by taking out this factor 2 to the power b and multiplying it with sigma f prime, you see that that must be equal to the coefficient in this formulation, which is equal to a. So when you look up in the book for, or online for data, in reference books, data regarding fatigue performance of a given material, then you can either see factors a, b, or sigma f prime and small b. And what matters, again, remember, when I take the log of both sides, then I will see a relation log sigma AR equals log sigma F prime plus B log 2NF. A linear relation between the log of fatigue life and the log of sigma F prime. Okay, this idealization again is not necessarily reality, but it turns out it's a very good idealization. Also, let us notice from this relation, as I have already said, that what we are observing here is sigma AR is equal to sigma F prime times the number of load reversals, which is twice the number of cycles to some exponent b. So you might ask, well, what if the stress amplitude is so large that failure occurs at the first load reversal? Now, we see from this expression that for that to happen, sigma AR must be equal to sigma F prime. Now, this is some type of a uniaxial loading, because first load reversal means you start loading the material, it increases, and just when you're about to switch and decrease the load, at the peak value of the stress, you have failure. So that's almost like a uniaxial loading. So this is almost uniaxial, say, tensile testing. And therefore, you might imagine that the stress value, which happens to be sigma F prime, should have something to do with the strength of the material. Now, there are different measures of strength, as we remember. There is the yield strength, there is the ultimate strength, there is the fracture strength. It turns out one of those values, namely the fracture strength, in fact, the true value, the true fracture strength is essentially something that is very representative of the value of sigma F prime that appears in the Baskin equation, the true fracture strength. So now we just keep that also in mind, because eventually when you look at the tables, or if suppose the value of sigma F prime was not provided, but you know the true fracture strength, then again you could do a quick back of the envelope calculation to make use of the Baskin equation. But this information also delivers us the following sort of hints. Now, first load reversal, so it's almost like a half cycle, is not quite high cycle fatigue. That is primarily the focus of the Baskin equation, or the stress-based approach. Well, what does the stress-based approach mean? It means that to predict the life, I'm making use of the stress value and not, let's say, strain. So the focus would be high cycle. That is where it's meant to work. Now, a single load, or half a load cycle in fact, or one load reversal, is not exactly high cycle. Now, the fact that this type of an argument even works, in other words, I put NF equals 1/2 or 2NF equals 1, one load reversal, and then I find that sigma AR has to be related to some sort of strength, and indeed it is indicative of the fact that probably the Baskin equation is not, although it's not meant for very, very low cycle fatigue, it is still perhaps representative of what might happen at low cycle fatigue. So this piece of information that we have, this observation, suggests that the Baskin equation might be indicative of low cycle fatigue as well. And it turns out that that is actually not a bad observation at all. Okay, so Now that we have a model at hand, the next thing that we would like to do is we'd like to quickly demonstrate it.